this is Captain Chaudhari. In my series of videos on basic stability calculations, today I'm going to do the calculation of position of center of pressure for certain defined shapes, right? For example, a triangular and semicircular shapes. So, as I told you in my last lecture that center of pressure actually should be better understood as center of thrust that is acted upon on a bulkhead because of the liquid pressure, because of the liquid being on one side of the bulkhead. What is the thrust that is imparted to the bulkhead, and where is that single point on the other side whereby if we support that point we are kind of supporting the entire thrust. So center of pressure should be understood as center of thrust basically. Now we had also said that for a rectangular shape, suppose the other side is full of liquid, right, and suppose the height of the bulkhead is h meter, the center of pressure is h by 3 from the base, right? So where the centroid of the triangle would be in case of a triangle. Now point to be noted is the centroid of the bulkhead is h by 2 from the bottom and center of pressure is h by 3. This usually you will see in different calculations that the center of pressure is generally below the centroid. Now we are going to look at two more shapes. To start with, the triangular shape. Suppose there is a bulkhead of shape like this, right? We know that the centroid is, suppose this height is h, the centroid of a bulkhead is h by 3 from the base. Yes, we know that. But let us find out where the center of pressure would be in case the other side of the bulkhead is full of liquid, right? So we'll follow the same principle. The center of pressure below the water level. Suppose this is the COP. Suppose this is the COP. The COP below water level, the distance of COP below water level is equal to moment of inertia of wet plane about the water level. This is the water level, divided by the area, that is the wetted area, multiplied by the depth of centroid. Depth of centroid we know is h by 3. So let's take the dimensions. Let's say h is equal to 9 meter and this is 8 meters, right? So a moment of inertia about the centroid axis parallel to base. Moment of inertia about the centroid axis parallel to base in case of a triangular shape is nothing but bh cube upon 36. Unit you know is meter raised to 4. But if we need to shift this moment of inertia to the water level, you know h is equal to 9, so this distance is 6 meters and this distance is 3 meters. So d that we use in the formula of theorem of parallel axis will be 3 meters. Area is base into height, 8 into 9 divided by 2, that is 36 meters square, right? So what is the moment of inertia about the water level? It will be bh cube upon 36, that is 8 into 9 cube upon 36 plus AD square. Area is 36, D is 3 square. So how much we have? This is 9 square and this is 162. So it is 162. That is the moment of inertia about the centroid axis plus 36 into 3 square, that is AD square. 324. So the total moment of inertia about the water level is 162 plus 324 divided by the area. Area is 36 and depth of centroid is 3 meters. Let us see how much it is. 162 plus 324 equals divided by 108 gives me 4.5 meters. That means the center of pressure is 4.5 meters below the water level. That is half of the H. So we may actually consider this to be a theorem, like in case there is a rectangular bulkhead without sounding pipe, right? The center of pressure is 1/3 the height of water column from the base. Mind you, there is no sounding pipe. And in case we have a triangular bulkhead like this, the center of pressure is halfway the height from the base or from the water level. So these two can be remembered as theorems so long as there is no water in the sounding pipe. And please understand, the water column in the sounding pipe creates a pressure which is equivalent to the pressure that is created by filling up the entire tank or entire hold. So that is the power of pressure because of the column. Now let's consider a semicircular shape, right? We must know about a semicircular shape or plane that the centroid is a point at which we can balance the plane. Suppose we make this semicircular plane horizontal and we balance at this point, it will remain balanced in equilibrium. So this position of the geometric centroid is 4r by 3 pi from the diameter. I sometimes tell my student 4 means captain, R means radio officer, 3 means third officer, and pi means second officer. So in case we have a semicircular shape whose radius is, say for example, 6 meters. Suppose there is a tank, and this tank, the side bulkhead is semicircular, right? So we want to know where is the center of pressure, and as I know, center of pressure will be usually below the centroid. So this semicircular plane, the radius is 6 meters. So how much is 4r by 3 pi? So that is 4 into 6 into 3 into 3.14. So 24 divided by 3 gives me 2.548 meters from the diameter. That is the position of centroid or geometric centroid of the semicircular shape. Now we have the usual formula that COP below water level is equal to moment of inertia, water level divided by the area multiplied by that of centroid, geometric centroid. So what is the moment of inertia about the water level, right? So here we know the moment of inertia directly about the water level, because in case if it was a complete circle, the moment of inertia about the diameter would have been pi d raised to 4 upon 64. But because this is semicircular, the moment of inertia about the same diameter would be half of thereof the moment of inertia of full circle. So this is the moment of inertia about water level. Divide by the area multiplied by depth of centroid. So pi d raised to 4 upon 64 into 2. That will be 144. That gives me 508.68. So 508.68. This 2 goes up, so multiplied by 2 divided by 3.14 into 36 into 2.548. So 8 gives me 3.532. So that is the distance of center of pressure from the water level. So we have seen that the center of pressure generally should be below the geometric centroid.